Okay. All right. This is part two. Angular acceleration, centripetal acceleration, tangential acceleration. We're just comparing all three of them and talking about all three of them and all that fun stuff. And then we're also throwing in a little bit of an extra part there as well. Okay, so let's start by looking at these types of accelerations. Angular acceleration. This is measured in rad per second squared. Centripetal acceleration is actually measured in meters per second squared. And fun fact, this is also measured in meters per second squared. So you actually have two types of acceleration measured in meters per second squared. This is rad per second. Centripetal acceleration, remember, isn't like it points towards the center of the circle, but it really is only serving to change the direction of velocity, not so much the actual value of velocity. Acceleration has two components. There's one that's either parallel. There's always parallel or perpendicular to path, to the path or to the velocity, okay? Or velocity. It's probably better to say velocity, okay? The component that's parallel to the velocity, so this would usually point with or directly against the velocity. We call it tangential, okay? And it is always a tangent to the path. That's why we call it tangential, right? This component is responsible for changing speed. So think of it like this is like the gas or the brake pedal in your car. Okay, if you go around a corner, if you go around a circle, this is like the gas or the brake pedal of the car. The component perpendicular to the velocity is called centripetal. Okay, and is always perpendicular to the path. Okay, the component this component is responsible for changing direction. Okay. Okay, so just to show you kind of, right, if you have no centripetal acceleration, you shouldn't be turning, right? But you can see that this is that with no centripetal acceleration, this is basically examples that we've seen before, right? Where either, constant speed or maybe you're speeding up as you're moving in the line or maybe you're slowing down as you're moving in the line, right? Depends on if your tangential acceleration is with your velocity or if it's against it, okay? Now, if you do have centripetal acceleration, then you should be moving in something of a curved path, maybe not perfectly circular, but it will be some sort of curved path. Do you notice that if you have centripetal acceleration but no tangential acceleration, you move in a constant speed around the curved path and you're turning, right? So what's happening is this right here is your centripetal acceleration, and that does nothing to the magnitude of your velocity. It simply changes the direction of your velocity. It's pulling the velocity. Okay, so you'd notice that at each point on this curved path, your centripetal acceleration vector might actually not look identical. Okay, you'll notice that it kind of curves as the object turns. Okay, it's trying to turn the velocity. It's always perpendicular. Here again, you're speeding up on the curved path. You'll notice again, this is going to go, towards the center of the motion that's being exhibited. Slowing down again, you're going towards the center of that motion. Okay, and I probably didn't draw that super well, but you can see that there. Okay, how do I get those two accelerations from velocity, right? I can actually prove this to you now because you know calculus, okay? Okay, so I'm just going to write what's going on in each of these steps here. So we've got this is my velocity vector, okay? The velocity vector is simply equal to the speed or magnitude of your velocity, okay, times the unit vector of velocity. You know what the unit vector is, right? You remember that from 2 units ago, I think. The unit vector is simply is a vector with a magnitude of one, but the same direction as the v vector, okay, as vector v. Now, this is really this unit vector, the v hat, that really only serves to give you the direction, but then we have to multiply it by speed magnitude to actually get the true length of the vector, okay? Okay, for the next step here, I'm differentiating both sides to get acceleration, okay? To get the acceleration vector, uh, differentiate, okay, differentiate velocity, okay, and we have to apply the product rule, okay. Okay, so to get the derivative of or sorry, to get a, we take the derivative of velocity here. Okay, so we're just taking the derivative. We do have to apply the product rule, which you're going to see down here in the last step. Okay, and now what's happened? Okay, is I've got this first term and I've got the second term, and I'm going to break it down for you by both terms. Okay, the term in the red here, this is dv over dt. Okay, and in this case, right, this is strictly talking about speed, right? Because this corresponds to this right up here, okay? And then the blue corresponds to v hat, okay? So this is dv over dt. This is really d speed over dt, so change in speed over change in time, and that's going to be tangential, okay? So that part, the red part, is dealing with tangential velocity. What about the blue part, though? The blue part you're going to see is dv hat. That's v hat. Can you see that? It's wearing a hat there. Okay, it looks kind of like a two-sided arrow. dt. Okay. Okay, and v hat does not define the speed, it defines the direction, okay? Because we said earlier it has the same direction as v but magnitude of 1. That's why we multiply it by the magnitude to give it the length that it needs to have, okay? So this is really d direction over dt. Okay, wait, change in direction is simply going to be change in direction is going to deal more so with the centripetal acceleration. Okay, is going to deal more so with centripetal acceleration. Okay, so that's how we get the centripetal right here. Okay. Okay. And then the final part that I want to go over really quickly is that you have, so at every twice differentiable point in a path, there is a best fit line, best fit parabola, and a best fit circle. Okay. And what's important to note is that each of these things do actually tell you something important about the motion. Okay. The velocity and tangential acceleration act along the best fit line. Okay. Or tangent. Okay. Do you notice that if you have, for example, maybe like at the bottom of the circle here, your velocity, so if you're moving this way, okay, along the path, so then your velocity would go tangent, it would follow that best fit line. So this would be v, okay, and it would also be a as well, okay? Or so I guess I could also say and a sub t, okay? The centripetal acceleration, okay, centripetal acceleration points towards the center of the best fit circle, okay, and you should remember that from physics 1, this is v squared over r, and then a sub c is equal to omega squared times r. These are both the same thing, okay? And you can derive one from the other just by recognizing that, v is equal to r omega. You can plug that into, you could plug r omega into there and you'll derive the other version of that. So for example, centripetal acceleration at the bottom here would point towards the center, okay? If you're maybe like up here on the path, then you would notice that your velocity would still go, straight up this way, okay? And so would your tangential acceleration, and then you might notice that your centripetal acceleration is now pointing, again, towards the center of the circle, okay? Okay, well, that's section 2. See, pretty short. Section 3 is even shorter, so stick around for that.